Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome back. Okay, now having got some idea of some of the power devices like power diode and the SCRs and also the GTOs, it is now time to look at another very important aspect that is related to the devices. Of course, we will continue with the devices, we have to do still the fully controllable devices like the BJTs and the Mosfets and the Igbts, but it is very important, relevant to at this point study what are the losses and how they impact the performance and the operation of a power electronic system. Now, as you know, a power electronic circuit is made up of several switching devices, controllable or semi controllable or diodes, as well as components like inductors and capacitors. Now, inductors and capacitors incur losses because of the presence of the parasitic resistance. Okay. Of course, the losses also take place in devices, but when we actually see the losses in devices and in the inductors and the capacitors, we find that it is the losses which occur in the devices which actually are most prominent, and therefore some time must be spent in understanding them. Okay, now the problem with the losses is that they manifest themselves as heat in a power electronic circuit. So, there are now two things. One is that we are losing in terms of the cost of the energy that actually corresponds to the loss that is taking place. So, basically this is a direct loss. The other is that when the heat is generated on account of these losses, it obviously is going to create problem for the device because the temperatures are going to rise, and unless this heat is flushed out quickly, the junction temperatures may rise and may eventually destroy the device and the rest of the circuit. Therefore, a cost has to be invested to actually be able to flush out the excess heat nicely and efficiently. So, there are these very major points because of which the heat management and the study of the losses is important. Now, we can broadly say that the loss determination that occurs because of the device operation in a power electronic circuit is actually required for two main reasons. One is that you try to compute the efficiency of a power electronic circuit by using the losses, and I can just straight away give you a formula that if I define the efficiency of a power electronic circuit, then I can say that this is nothing but equal to the output power by input power, or I can just write it there as output power PO divided by output power PO plus losses. Okay, and if I multiply this by 100, then I get losses in percent. So, basically now the point is that we need to determine these losses, and once we know the losses, we can find out the efficiency. Okay, so that is the first thing, we want to determine the efficiency of the power electronic circuit. So, that is one reason for determining the loss. The second reason is, if I may say, it is the design of the thermal management for the PE circuit. So, that is another reason why we need to determine these losses. Now, the design of the thermal management for a power electronic circuit, it actually could be simply just trying to design a heat sink, or it could actually involve heat sink plus some force cooling through fan, So, if you remember in the first couple of lectures when I some power electronic systems, I did show you the heat sinks and the fans which are used for forced cooling. Now, among the very latest addition to the thermal management systems are where people are using water conduits in the heat sink. So, basically there is a water flowing also which actually gives the additional cooling. So, water cooling plus heat sinking. Now, in order to set up a situation that will naturally give us an opportunity to understand the prominent loss mechanisms in the power electronic circuits, let us discuss the issue of voltage regulation, which requires that the output voltage of a power converter is held constant. Maintaining the voltage constant or fixed faces certain challenges. One of them is that the input voltage. For example, if we are trying to get the basic voltage from an AC voltage source after rectification and the AC voltage changes, then my voltage changes. Okay. So, input voltage say AC changes. The other problem is that the load conditions might change. The need for keeping the voltage constant under these conditions can be actually understood by understanding or reviewing the definition of an ideal voltage source. So, if you actually have a ideal voltage source, let me just mark this as Vs, and let us say that its internal resistance, the source internal resistance is actually 0. Okay. Now, irrespective of the load that I will connect across this source, the voltage across the terminal A and B of the load will always be equal to Vs. But this kind of ideality, it rarely happens. So, if you actually try to equate the power electronic circuit which is giving out a certain voltage output which you want to apply to a load RL, there will be several drops in the circuit. Okay. As we just saw that the inductors and the capacitors will have parasitic unwanted resistances which will actually cause the voltage drops, and similarly there will be devices which are also going to cause the losses and the drops therefore. Okay. When the load changes so as to draw more current, okay, and my voltage source is now in a way no longer ideal, which means that my Ri is no longer 0. So, Ri is now finite and non-zero. So, basically the voltage across the load RL will tend to change, and that is another reason why I would like to do something to maintain the voltage constant, because my load RL may be sensitive to variations in the voltage. Okay, now what is the solution? Please recall that we had in the first or the second lecture we had talked about what is called voltage regulation. Now, when we say voltage regulation, at that time also explained that it means it is nothing but you are trying to hold a voltage constant as determined by a set point or a reference value. Now, there are some passive and some active ways of doing voltage regulation. Some of the very basic ways of keeping the voltage constant are, for example, the use of a potential divider system. And how it will look like? So, if there is a supply source Vs and I have just put a network of these resistances R1 and RL, where RL is the load, is the resistance which is representing my load, then the voltage Vo that will appear across RL can be given by simply Vs into RL divided by R1 plus RL. Okay, so this is one way we could keep this output voltage constant for a given voltage supply. But the problem is that once you fix these resistance values, you can actually keep it fixed only at a given value. You cannot change this VO at some other value. So, you cannot keep it constant at some other value. So, this is the limitation. Now, in most of the electronic controls, this is not going to work because we need to actually be able to control this voltage almost to any value electronically without having to change anything manually. So, here if you want to do something on this, we will have to either change the values of R1, okay, and then probably tune it again, design it properly and then apply it. One of the other problems is that the losses which will take place in the resistive network. Another commonly used method for the voltage regulation is by the use of a Zener diode. Now, I briefly mentioned about the Zener breakdown when I was talking to you about some p-n junction mechanisms, okay, and we will return to this topic a little later with more details. Now, when we say the use of the Zener diode, so what I do is I just connect a diode which is capable of Zener breakdown, which has been so designed, and let us say this is my supply, and the Zener it has a certain voltage breakdown voltage as Vz. Then if I actually apply my load resistance right across the Zener, we will find that the moment the Vs it tries to go beyond a certain value, my Zener diode will break down and actually it will hold the value at that Vz. So, Vz is what is going to appear across RL, and assuming this is what we want the voltage to be across the load RL, then this will do my job. But the problem again with this is that the breakdown of the diode, this is in a diode which actually is going to cause large current and hence losses. So, usually these high currents are actually prevented by inserting appropriate resistive networks, which actually again cause a loss of energy in the system. So, these are all convenient low power solutions. When you go to very high power, these become a bit prohibitive, okay, something which is more reliable, something which can work and operate over a wide range of situations. Okay. So, that is where the closed loop voltage regulation, which I explained in the first lecture, it comes up. So, when we say a voltage regulation problem, I will just quickly draw again my PE converter or the PV circuit, and let us say this is the output voltage VO, and there is a input voltage Vi. Now, this could actually be obtained either from a direct DC source or it may be coming after rectification from an AC voltage which may be subject to variation. And I told you that if the AC voltage will vary, the Vi would vary, which we are applying to the P converter, and so output voltage VO will vary as well. Okay. So, what is the way of handling this? You just sense the output voltage VO, you compare it with some set point which corresponds to the reference voltage that you want your output voltage VO to be held at. Okay. You just call this, let us say, VO reference, and this is nothing but an error amplifier. So, it just tries to see how far or how much away is your actual output voltage from the reference voltage. Based on that, and also using certain concepts which are used in closed loop control systems, it actually gives out appropriate signal to a controller. Okay, now, this could be an analog controller or it could be a digital controller, as we have told you before. The output of this controller then actually manipulates appropriately the P converter's control variable. So, whether it is the switching time, okay, or whether it is a frequency, it actually plays with that control variable. So, let me just mark this as Vc, okay, and that is in response to this feedback system, closed loop feedback system, my PE converter will then operate in a direction so as to move VO, so as to actually generate VO closer to VO reference, and within a certain time period, within a certain duration, VO will actually become equal to VO reference. Okay, now let us just take the examples of linear regulators and the switched mode power supply, which exhibit a stark difference between the losses incurred by them, a fact which has revolutionized the field of power electronics. These supplies are fed by an AC source, okay, usually, and you have this transformer, because the voltage that is actually coming from the AC line, okay, it may be very different from what exactly you want at the output. So, you may have to actually transform it using a transformer, and after this transformation, if you remember the lecture number 1, I did give you a very hypothetical example of this, and then this pass, the output of the secondary side of the transformer is actually fed to a rectifier, and that is how you get this voltage. So, basically if you recall, we got a voltage with some ripple, and we said that this ripple could be minimized by putting appropriate values of the filter components like capacitors and inductors. Now, the question is that this is still what you see here, I will just call it as a raw voltage, because of reasons that it is not regulated, not only because it has lot of ripple, but also because if the AC voltage varies, there is no mechanism that this system will automatically keep itself a constant value of voltage. Okay, so what is the solution? Now, there are two ways in which people can approach this problem. So, basically from this VO raw, I want to obtain a nice VO constant, which will be constant, which can be applied to my load. Okay. So, there are two approaches now which are taken from here. One of them is what is utilizing the linear regulators, okay, linear regulators, and the other what is actually utilizing what is called the switch mode regulator. Let me just briefly tell you about these two, and then we can come back. I know that I have deviated a lot from the initial topic of losses, but let me just first do this explanation for these two types, and then it will be very easy for me to explain to you the consequences with losses, and this actually is fairly general. It is applicable to almost all classes of power electronic circuits. So, that is the very important advantage of doing this. Let us say that this VO raw, let me just call it as VI, because I am now going to input it to the next stage of a linear regulator. So, VO raw is equal to VI for the subsequent explanation. Okay. So, VI, and here if you see I am putting one series pass transistor Q. Okay. Now, I know that I have not yet fully covered the bipolar junction transistors or field effect transistors, but let us rely on our knowledge that we have obtained earlier about transistors. Okay. So, we all have at least this basic knowledge about transistors to be able to understand what I am going to say now. Okay. So, let us say this VI is now applied through the series pass transistor to a load, and again I represent this load by RL. And let me just say that there is a resistive network here which I am going to mark as R1 and R2. Okay. Now, if I can take the output, let us say from this potential divider network, okay, and this has been calibrated in such a way that this whatever I am just tapping through this red wire is actually going to correspond to the reference voltage, the voltage at which or the voltage which must appear across the load. So, let me just say that this is VAB. Okay. Now, if you basically if we pass this to an error amplifier, just like what we did in the voltage regulation case, and we compare it with a reference voltage, okay, then the output of this can be used to operate the base of this transistor Q. Okay. Now, this is a very simple compact system, very simple circuit, and you will see that the Q will actually drop a voltage across its collector and emitter appropriately, so that what appears at terminals A and B is equal to the reference voltage or some scaled version of that, some calibrated version of that. Okay. So, such is the simplicity of these kind of systems, that they can actually be realized easily as simple circuits. They are very convenient because they can be actually realized over monolithic ICs, and you can actually have standard values of the output voltage which they can give you once an input voltage is applied. Okay. But what is the issue? The issue is that this system will incur very high losses. Okay. So, what will actually happen is that we will see with the help of an example, but broadly speaking it is the drop across this transistor Q which actually is going to operate in what is called the active region of operation. This is going to work just as a variable resistor, and depending on what voltage I need across the terminals A, B, this resistor will drop appropriate voltage across it, okay, and therefore you have the desired voltage across A, B. So, let me just now give you an example. It is very common for these linear regulators to be actually realized as what are called 3-pin regulators. So, there are 3-pin 5-volt regulators, 3-pin 15-volt regulators, and so these are all standard voltages. Okay. And one of the things that why we are actually calling it a linear regulator or why we call it a linear supply, actually you might have guessed already that because the transistor is operating in the active region, which is the linear region, okay, that is why these supplies or regulators are also called linear regulators. Okay. So, let us say we have this a 3-pin regulator, of let us say 5 volts, and Vi that we are applying here, okay, let us say it is 11 volts maximum. So, as you know, there will be ripple from the what we got initially, the VO raw, and let us say that the maximum value we get is 11 volts there, 11 volts. Now, the regulator is 5 volts. So, basically at the output, if I just show this by resistance RL, my 5 volts is going to appear here. Okay. Now, let us say that the rated condition, okay, the output current that the load will draw will be 12 amperes. So, at 5 volts it will be drawing 12 amperes. So, basically what will happen now? You will see that our transistor Q, which we have seen before in the previous circuit, Q will drop an 11 minus 5 volts, which is actually 6 volts across it. And now, if 12 amperes is going to flow through this transistor into the load, then basically we can say that the power loss across the device Q will be nothing but, so let us say P device or PQ is nothing but 6 into 12. Okay. And what is the power output? Power output, so this is PQ and this is PO, is nothing but 5 volts into 12, so many watts. Sorry, I should write a watt here also. Okay. So, now what will be the efficiency of this system? The efficiency of this system will be, we can obtain by using PO divided by PO plus PQ, as we have seen before, and if we do this very simple calculation, we can say 60 over 60 plus 72, and if I just multiply it by 100 to get the efficiency in percentage, I get a very poor efficiency, 45.5%. Okay. Now obviously you can see that nearly 55% energy is getting wasted in this process. Okay. Now as the power levels go high, this obviously is not an attractive bargain, but we actually have a very wide range of application where we need very high power levels as well, where we need to hold the voltage constant. So what do we do? Okay, so now let us just draw another circuit. So let us say your Vi, same as the linear regulator example we took, it is a rippled output voltage that we are getting after rectification of the input AC supply, let us say, and this is the input side, and then let us say that we have a transistor, again a transistor Q, and let us say we have a resistance or the load resistance RL, across which we need a constant voltage VO. Now instead of operating the device Q in the active region, now let us say we actually operate this device Q in on off manner. It is also called the switch mode manner, because actually you are using it as a on off switch. Okay. Implication of this will be that across RL I will get a pulse of this type. Okay. So when the Q is on, you have the input voltage Vi appearing across RL, and when the Q is off, you have a 0 voltage appearing across RL. Okay. Now this we could try to maintain by controlling the switch Q in a manner that I can still get a nice and constant output voltage, but there are some challenges. The challenges is that, as you can see, there is a huge amount of ripple. The voltages are really varying from Vi to 0, very wide ripple. So this is the price now we have to pay if we have to use this kind of a switch mode operation of the device. Okay. We will see the advantage of this in a minute, but the issue is that I cannot apply this kind of such a high rippled voltage to the load. So what we can do, somebody would obviously try to add one capacitor. If I use a capacitor, depending on the frequency at which these waveforms are going up and down, my capacitor value will be chosen, and it will definitely make this thing only maybe it will be actually something like this. It will go like this, like this, like this, like this, like this, like this. So this is what we will get. Okay, and more is the value of capacitance, less will be the ripple in this voltage that we have shown. So this is my VO, which is across RL. Okay, now there is a problem with this circuit. The practical problem with this circuit is that if I put a capacitor here to reduce the ripple of the voltage that appears across RL, then the problem is that the moment I turn on my switch Q, there would be a sudden large current that will flow in the circuit, because the capacitor is uncharged and behaves like a short. How do we prevent it? We cannot put a resistance to limit the current, but we can definitely put a inductor to limit the current, because the inductor will not cause any loss. We know that the current and the voltage in an inductor are 90-degree phase apart, and if you actually try to get expression for the active power, you find that it actually turns out to be 0 because of this phase lag. So this is precisely what is going to happen. So if I actually add one inductor here, it will take care of this very large infinite current problem. But the moment you put an inductor, and as you can see the Q, the transistor Q is coming in series with the inductor, now I must provide an alternate path. If my inductor is conducting, there must be an alternate path provided when I switch off device Q. Okay. Now usually this is what we will do, this is the most common way of doing it, that we put actually a diode in this manner, which provides an alternate path for the inductor current. Okay. So basically by doing this explanation and by looking at the compulsions that we have of doing this, of actually regulating or controlling the output voltage, in this manner we actually ended up with this circuit, which is actually a chopper circuit or a simple step down DC to DC converter. We will return to this topic again in due course. Okay. So, now if I see the output of this circuit, of course depending on what values of C and L I use, I can always make it nice. So, it will be very nice with low ripple, we can actually do a very nice thing, but it is a non-linear system. It is a highly non-linear system because your device is now not operated in a linear region, but actually it is used as a switch going from on state to off state. So, switch mode power supplies or non-linear supplies. Now, if you look at the typical operation of this switch, the switch when it is conducting, okay, so I am sure you know from your previous background of even low level transistors that when the transistor is on, when it is conducting the current, it actually will drop what is called VCE sat. Okay, the collector emitter saturation value is what this transistor will drop. That is when the transistor is conducting, when the Q is actually on. Okay. So, you will have a voltage which will be very small. Now, VCE sat as we know is very small. Typically for low level transistors 0.2, 0.3, while for power transistors which we are going to see in the next 1 or 2 lectures, it will actually be more. It will be probably 1 volt or 1.5 volt or even higher. Okay. So, the situation is that when my current is maximum, my voltage is very less. So, this is actually just VCE sat. Okay. And when, so I can even say this current, conducting current as IQ, and when my switch is off, that time we will say my current is 0, but my voltage across the device would be maximum. So, if you remember the transistor, when it will be turned off, the entire voltage will come across it while it will be conducting negligible current. It is actually nothing but the saturation current, which can be almost neglected from the analysis. So, what you see, whether the device is conducting as in A or when it is not conducting in B, the product of the voltage and the current remains very small or nearly 0. Okay. Now, this was not the case in the linear regulator case, where the transistor is always in the active mode and always dissipating power. In the case of the switch mode regulators, this is not the case, and this is directly a result of using the device Q in the on off mode. Of course, the price we have to pay, as I said, is a non-linear control, more complicated than the linear regulators, and the use of the filters which actually require additional components like the diode to appear in the circuit. Now, we will do more of these things when we look at more of these switch mode power supply configurations. When we will come to it and see more details, we will come to these things again. Now, the characteristics that you see here when the device is on or when the device is off, these are also called static. Okay. Static. So, these are static characteristics, or we can say this is the static performance of the switch Q. Okay. But when we actually go from one state to another, when we go from one static state to another static state, like for example this VCE sat, the moment the device turns off, it actually has gone up. Okay. So, this is the voltage that it is blocking, the applied voltage maybe. And if you see here, there is a transition from full current to negligible current. So, this is the phase, this transition phase that you see between the two static portions of these waveforms. This is called the dynamic region or dynamic performance of the switching device. These are also called the switching performance of the device, because we will just see that it has got a direct consequence of the losses. So, basically what we can conclude from what we just studied, we can say that though the static performance, which is also given or denoted by or represented by conduction losses, are very small, okay. Similarly, when the device is not conducting, that time also the losses will be negligible, since the reverse saturation current or the leakage current as it is called is very small. But it is during the transition from the conduction or the static phase to another static phase, during which there is a power loss which is taking place. And what is the power loss? If I just use the previous sheet, I can say that my power loss will be given by this, because this is the place where my product of voltage and current is not 0, it is significant. And if I just denote this by time t1 and t2, and if I just denote my voltage and current during this time by V and I, then I can just simply say that the instantaneous power, okay, during this switching operation can be denoted by V into I, okay. So, this is the instantaneous power, and if I want to determine the energy corresponding to this loss which will take place, then I can just simply say it will be T1 to T2 V into I dt, and I can just say that because this is done when my device is turning off, I can just say E off, and this is the turning off of the device, where I have denoted voltage and current during this transition phase by V and I. Now, there are people who often use just a T off to denote this interval T1 to T2. So, therefore, we can even modify this by saying this can be 0 to T off. So, we will get E off like this, and then if we just multiply this by the frequency of operation, which will just show how many times these energy losses will occur, how many of these transitions will be there in 1 second, I can then get the total loss in joules per second or watts, okay, due to the operation when the device is turning off. Now, we can find that during the turn on process also similar loss will take place, and that can be actually denoted by simply E on, okay, and we will get a similar expression. Okay. Now, there are cases like, for example, when we were doing power diodes, we have seen that it actually leaves a tailing effect, or it actually has the problem of reverse recovery charges. Now, in most of the data sheets, okay, this information about the loss during the reverse recovery time, the loss during the switch on transition, the loss during the switch off transition, which are given by E on, E off, and maybe ERR reverse recovery, they are provided in the data sheet. So, if you are operating at a certain frequency f your circuit, you have to just multiply by f to get the total switching losses. So, P switching loss, I can just say now frequency multiplied by E on plus E off plus ERR. Now, if ERR is not there, if it is not important, then it may not be there. Okay, so, this is how somebody can find out the dynamic losses or the switching losses when the transition is taking place. Likewise, the conduction losses can also be computed. For example, if the switching device happens to be a bipolar junction transistor, its on time conduction losses can be given by the following expression. So, P conduction during the on time of the device is nothing but the product of VCE SAT value of the device into the collector current average value or the DC value, where IC average we can write as 1 over T integral of 0 to T on I of T dt, and then we can just get this value of the P conduction on. Now of course, while deriving this integral, we can take help of the actual waveforms of the system. So we know what kind of current and voltage waveforms are appearing across the device, and then we can compute this expression by actually plugging in the values of or the expression for I of t. Now it should be noted that the P conduction off, so during the off time of the device, ideally we should not be saying these are conduction losses, but then we treat the static losses as conduction losses. It is a special case of conduction where I is 0. Okay, so this P conduction off can be safely taken to be equal to 0 in general, because the reverse current or the leakage current is very small, and that is the current that will be flowing during this off state. Now the expression for the conduction losses for the BJT, the Igbts and the Mosfets, the 3 major devices that we will be dealing with, they are actually shown on your screen. The various terms which are used in these expressions would become more clear in the upcoming lectures. Now having studied these various aspects leading to the losses, now this is of course the example we took is of a switched mode regulator, a switch mode regulator and a linear regulator, but please understand that this switch mode regulation is actually a phenomenon which is used throughout. So basically this is also used in DC to AC power converters. There are also switch mode converters, okay, and several other places. So basically this should actually enhance the understanding about the kind of losses which take place in power electronic circuits and may actually help us to design the systems better. We will see other aspects of, now we will get back to the power devices, the remaining power devices in the next session, and we will see what the various devices have to offer in terms of their performance. Thank you very much for your attention.